Hi, everybody. Let me thank the organizers to giving me this opportunity to talk for you about my recent talk. Here is the sketch of my talk, the motivation, and then elliptic surface module lattices, and our result. Well, the motivation of this work is come back by the work of Shioda. So let K be, oh, sorry. So let K be a number field, and capital K denotes the function fields of projective line. By an elliptic curves, I mean an algebraic curves of genus 1 given by these equations, where the coefficients are in the capital K in the function field. And this polynomial, which means the discriminant of the curve is non-constant. So the set of K rational points is an finitely generated abelian groups. This is proved by Lang and Neron. And it means that it is isomorphic to, it is isomorphic to a finite group, which is called the torsion group of the, this group, and some copies of Z. And the number of the copies is known as the rank of elliptic curves over K. So the torsion part is well defined and classified for any elliptic curves over function fields, but the ranks is very complicated to study. Here is the definition of splitting fields. It means that a subfield of the function fields for elliptic curves over K of T, this is the number field, the smallest subfield of the complex numbers, which contains the number field K, and we have this isomorphism. It means that the group of the CT rational points on elliptic curves is isomorphic to the group of the K of T rational points on elliptic curves. So the largest known rank for the elliptic curves over CT is the family is 68 for M, 316 for the Shioda family, which is given by this equation. So this family is introduced by Shioda and is studied in some of his papers. But in a series of 4 papers, we studied the structure, I mean the lattice structure of this group for all of the M's. And he realized that the generators of the lattice comes from this type of elliptic curves together with some other rational elliptic curves, or I mean some rational elliptic surfaces. But in 1999, Shioda gave a statement as in some of his papers that the splitting field Km of this family is a cyclic extension of a cyclotomic field, and probably the minimal section, I mean the minimal vectors in the lattice, in this lattice, give a subgroup of finite index in the unit group of this number field. So this remark was the origin of a big computational project which we started in the middle of the pandemic. And the idea was, determine Km, the splitting field of this family for all of the M's, and also determine a set of independent generator for this lattice or this group. In a joint work with my colleague, we started by studying this family, which is which give us KT surfaces for all N, and we try to determine Kn, the splitting fields and the generators of this group. So for any elliptic curves, our one variable function first, it is associated an elliptic surface. I mean a morphism from a complex surface to P1, which is determined by the codirected neuron model of this elliptic curve over K. Here, SOE is a complex, smooth projective surface, and P is relatively minimal vibration with generic fiber E. And we assume that P is not smooth. At least there is one singular fibers. So the set of the K, capital K rational points can be identified with the sections of this morphism. I mean the morphism from P1 to SOE. That satisfies this equality. So for any P point, we denote by this the image of the corresponding global sections. I mean, this is the section on the neuron codirected model of the elliptic curve. So the point, the identity point of this group corresponds to a zero section. Using the equation defining the generic fiber, one can classify all of the elliptic surfaces in three kinds. If we have these equations, and using the degrees of A out T and B out T, one can say that it is rational if A out T has degree less or equal 4, and B out T has degree less or equal than 6. It is called K-T surface if we have these inequalities. So otherwise, it is called the honestly elliptic surfaces. For example, for the Schroeder curves, for M between 1 and 6, we have rationals, elliptic surface, and for M between 7 and 12, we have K3 surfaces, and otherwise we have an honestly elliptic surface. For our family, EN, it is actually K3 surfaces, elliptic K3 surface for all our N between 1 and 6, and for larger integers N, we have honestly elliptic surface. So the theory of model lattices structures on elliptic surface introduced by Shioda in 1990. Given any elliptic surface, our projective line, let NS our SOE denote the neuron severity group, and TB its trivial sublattice. It has a lattice structure, so the trivial lattice is generated by the zero section and all of the reducible components of all fibers. So Shioda proved that there is an isomorphism between the group of CT rational points and this quotient lattice given by this map. And so this isomorphism introduces a pairing on these sets, which is given by the intersection numbers. So this lattice structure is known as the model wave lattice structure of E over C of T. If we let denote by P of S of E the rank of the neuron severity group, I mean the Picard numbers, then Tate and Shioda gave a formula for determining the model rank, I mean the rank of this group, using the Picard numbers and this sum, which is all of the singular fibers. So since for rational and the K3 surfaces, we have Picard numbers 10 and 20, so the model rank or rank of this group can be less or equal 8 and 18, respectively, for rational and K3 surface. And for other cases, we have larger than 19 for honestly cases. But up to now, the largest known family is for the Shioda curve with the power 316. I mean, some multiple of this number. This is determined by Usui and proved, stated by Shioda and proved by Usui. For this number, we have the maximum rank. So the family En is introduced by Shioda in 1998 and studied the lattice structure on this family. He proved that for these n's, between 1 and 6, the ranks of this lattice are equal these numbers. So the largest rank is 16. Moreover, the generators are this type, our polynomials, our rational functions in the K, in the CT. So, but he didn't give any idea how we can determine these coefficients, which are all complex numbers. So, in some of his earlier papers, he considered the case E2 and determined the splitting field as this one, which zeta 3 is the surge root of unity, and this point generate the lattice. So our work is determine the splitting field and the generators for this family for other n's. For n equals 3, we have this theorem. If we let alpha 1, alpha 2 be this complex number, then the splitting field is equal this one, and the points are given in this form, and also 4 point this form, and the other 4 points comes from some transformation given here, where the coefficients are here. For n equal 4, we have, if we let zeta 8 and zeta 12 be this roots of unity, then we have this isomorphism. So K4 is this number field, where we have these complex numbers, and the generators are given by this rational function, where the coefficients are the next slide. Here we have the rank equal 12. So we have 12 points with these coefficients. So the difficult cases are for n for 5 and 6. If we let this zeta 5 denote this complex number, which is root of unity, and zeta 12 this, and we consider these units in the field determined by these complex numbers here. So we have this isomorphism. It means that this is the splitting field in this case, and we have 16 points that generate this lattice. We have these coordinates for our points. For the coefficients of those points are determined here. If we let U1 to U8, these complex numbers, which all are some multiples of units in the splitting fields, and if we let this quantity, this complex number, then we have the coefficient listed here, which are practically they are a very big complex number with nested radicals. So we try to show by some notation. In the case n equals 6, if we let beta 0 and beta 1 denote this complex numbers, so we have the splitting fields generated by this, where here V is a root of this polynomial. And we have so this isomorphism and the 16 points, Pj and Pj plus 8, which have these coordinates of this time. The coefficients are very big. I didn't include it in the slides. But here I'm going to give an idea the proof I know. Actually, in Shioda in his theorem introduced certain elliptic surfaces, rational elliptic surfaces, and by studying on this rational elliptic surface, he determined the model lattice structures. So the idea of the proof for n equal 4 if we consider this rational elliptic surface, and then we can determine its generated, then by certain transformation we can get our theorem for our this elliptic curve. So the idea is determine firstly the generated and splitting field of certain elliptic surfaces, and then try to change the coordinates to our elliptic curve En. So in this case, by letting our En prime, the lattice structure is isomorphic to the root lattice to allow the root lattice. So the points are this form. There are 54 points this type. Substituting the coordinate, we have 4 relation, and then using this, we get 2 polynomials in terms of P. And then taking result on these polynomials in respect to P, we have a polynomial here of degree 27, which can factorize in this form. So any root of these polynomials rise and point, 27 point in the group of E4 prime. So by searching for 6 independent points, we have to take the intersection numbers of these points and try to find some of them that has determinant. The Gram matrix has determinant equal to the given in the Schrödinger theorem. So the idea of the proofs are similar, and in all of the cases we have some rational elliptic surfaces, and here. Okay. The difficult cases were the case n equal 5 and 6, where we have to split 2 polynomials of degree 214, which was a very difficult cases in our work. So at the end, here are some references. Our work is available in the archive and is submitted. So